Hi guys, in the previous lecture we covered the concepts related to a single phase transformer in which we saw different concepts like equivalent circuit of the transformer, efficiency and the voltage regulation of the transformer, the ratings of the transformer, harmonics in case of a transformer. So in this lecture what we will be doing is we will be solving some GATE previous year problems that have come from the single phase transformer. So let us get started with our first problem. In our first problem, it is saying that two transformers of the same type using the same grade of iron and conductor materials are designed to work at the same flux and current density. Okay, means Bm is constant and J is also constant. But the linear dimensions of one are 2 times those of the other in all respects. Okay, dimension of one is equal to 2 times dimension of 2. Now the ratio of kVA of the two transformer closely equals. As I told you, kVA rating is proportional to dimension raised to the power 4. That means kVA 1 by kVA 2 is equal to dimension 1 by dimension 2 raised to the power 4 equal to 2 raised to the power 4, that is 16. Okay, that means the ratio of kVA rating of both the transformer is equal to 16. The kVA rating of first transformer is 16 times the other transformer. So remember, when we scale, these conditions are very important. Whenever scaling is done, it is made sure that the magnetic flux density and the current density are kept same. Why current density is kept same? So that electric field is also same. Okay, so both these things are kept constant while we scale the dimensions of transformer. Let us move on to the next problem. In the next problem, it is saying the efficiency of 100 kVA transformer is 0.98 at full as well as half load. Okay, for the transformer at full load, copper losses as compared to core loss is. So what we studied, efficiency is equal to x kVA cos phi by x kVA cos phi plus pi plus x square PCU FL. Now x is the loading of the transformer. So when we talk about full load, that means x is equal to 1. So efficiency is 98%. So we can keep 0.98 is equal to kVA into cos phi. Since we are given nothing about the power factor, I will assume it to be cos phi. kVA cos phi plus pi plus PCU FL. So if we solve this equation, we will get pi plus PCU FL is equal to 0.02 kVA cos phi. This will be my first equation. Now it is given at half load x will be 0.5. Efficiency is again 98%. I am assuming that power factor does not change. Okay, x kVA cos phi, then x kVA cos phi plus pi. Now x square will be 0.25 PCU FL. Now if we calculate from here, pi plus 0.25 PCU FL is equal to 0.01 kVA cos phi. Now we have two equations in pi and PCU FL. If we solve these two equations, we will get pi is 0.006 kVA cos phi and PCU FL is 0.0136 kVA cos phi. Now if we see here, PCU FL is greater than pi. That means at full load, copper losses are higher than the core losses or the iron losses. So that is what is our observation from the given data, that efficiency at full load and half load is same at 98%. Okay. So remember this expression for efficiency. This is pretty much important. And remember, what does X denote? X denotes the fractional loading. Moving on to our next problem. It is desired to measure parameters of a 230 by 115 volt 2 kVA single phase transformer. The following wattmeters are available in the laboratory. Okay, we have been given 4 wattmeters. Now these wattmeters are used in short circuit and open circuit tests respectively. Which one to be used in OC and which one to be used in SC. Now first of all, if we remember open circuit test, then open circuit test is conducted at no load. That means the no load current will be measured by the ammeter, or no load current will be flowing through the wattmeter. Okay, and I know no load current is 5 to 8% of full load current. That is, no load current is very small. So we can use a wattmeter which has a lower current rating. And if we remember cos phi naught, the no load power factor is also very small. It is around 0.2. Okay. So we need a wattmeter which has a lower current rating and it has a low power factor. That means we can use this wattmeter. Its current rating is 5 ampere and its power factor is also low. Next, if we want to conduct short circuit test, we know that short circuit test is conducted at rated current. So let us find out what is the rated current or what is the full load current. So short circuit test will be conducted at high voltage side. So let us find out full load current at high voltage side. It is 8.69 ampere. So we need a wattmeter which has a current rating higher than this. That means we need a current rating of 10 ampere. And power factor at full load will be higher. So we need a wattmeter which has a higher current rating and a high power factor. That means this one. Okay. But if you see, the voltage is 150 volt. Why? Because in the under short circuit test we only apply a low voltage, because a low voltage is required to flow a rated current under the short circuit condition. The voltage required is not high. Okay. So means for open circuit test we need W2 and for short circuit test we need W3. Okay. Under short circuit test power factor is higher, under open circuit test power factor is lower. In our next problem, it is given that a single phase transformer has a turns ratio of 1:2. It is connected to a purely resistive load as shown in the figure. The magnetizing current drawn is 1 ampere. The secondary current is 1 ampere. If core losses and leakage reactance are neglected, what is the primary current? So if we draw the phasor diagram, I will take I mu in the same phase phi m. EMF induced will be lagging like this. Since 1:2, E1 will be smaller than this. E2 will be higher than E1. We have connected a resistive load here. That means the current flowing will be in same phase as voltage. So let us say this is my I2. Now I1 by I2 is equal to 2. So I1 will be higher than I2. Let us say I1 dash. Now we know that primary current is phasor sum of magnetizing current and load component. This will be I primary. Now I1 dash is equal to 2 into 1, 2. I mu is equal to magnetizing current is equal to 1 ampere. So if we want to find I primary, it will be under root 1 square plus 2 square, which is 2.24 ampere. This we have obtained from the phasor diagram, that the primary current drawn is phasor sum of the magnetizing current and the load component of the primary current. Load component of the primary current and the secondary current are related by the turns ratio. Okay, so this is the current drawn by the primary. In our next problem, it is saying the low voltage winding of a 400 by 230 volt one phase 50 Hz transformer is to be connected to 25 Hz. What should be the supply voltage? Low voltage winding means this 230 volt winding. Okay. Now we have made the frequency 25 Hz. I want to know what is the voltage. Now when we are changing the frequency, if we are reducing the frequency, then if we see V by F ratio will increase. V by F ratio will increase, due to which magnetic flux density will also increase, which can cause saturation. Okay, transformer may saturate. That means we have to keep V by F is equal to constant. That means V1 by F1 should be equal to V2 by F2. So 230 by 50 is equal to V by 25. It implies voltage is equal to 115 volt. So the supply voltage should be 115 volt on the low voltage side at 25 Hz frequency, so that magnetic flux density remains constant and transformer does not saturate. Okay. In our next problem, it is saying voltage is equal to 400 sine 314.16 t is applied to one phase transformer at no load. No load current of the transformer I naught is given to be 2 sine 314.16 t minus 85 degree. We need to find the impedance of the magnetization branch or the shunt branch of the transformer. Now if we represent them in terms of phasor, it will be 400 by root 2 angle 0, and I naught will be 2 by root 2 angle minus 85 degree. Now the connection of the shunt branch is like this. Here current I naught is going, here voltage V is applied. To find the impedance, we will do just V by I naught. Z naught is V by I naught, which will be 200 angle 85 degree ohm. Okay, so this will be the impedance of the shunt branch in case of transformer, or we can call it as the magnetization branch. Okay, this is the impedance. In our next problem, it is saying a 50 Hz transformer has equal hysteresis and eddy current losses at rated excitation. That means hysteresis loss is equal to eddy current loss is equal to P. Now it is being operated at 45 Hz and 90% of the rated voltage. We need to find by how much the core losses will change under this condition. Now, in our first case, V by F is equal to rated voltage by 50 Hz. In our second case, V by F is equal to 0.9 times rated voltage. It is saying 90% of rated voltage by 45 Hz, which comes out to be V rated by 50. Okay, that is V by F is constant. Okay. Now we need to find how the core losses will change. We know whenever V by F is constant, hysteresis loss is proportional to frequency, eddy current loss is proportional to frequency square. Now frequency is being made 0.9 times. Okay. Since frequency is being made 45 Hz from 50, that is we are multiplying by a factor of 0.9. So how much hysteresis loss will become? It will become 0.9 P, and eddy current loss will become, since it is proportional to frequency square, 0.9 square P, that is 0.81 P. So core loss or iron loss will be PH plus PE, that is 1.71 P. Initially core loss was 2P. So delta Pi is 0.29 P. If we want to calculate in terms of percentage, 0.29 P by 2P into 100, that is 14.5%. So core losses will reduce by 14.5% if we make the frequency as well as the voltage 90% of their initial values. Okay, so that is how you have to derive the proportionality. First of all, whenever we are talking about hysteresis and eddy current losses, you have to check whether V by F is constant or not. If it is constant, then you will use that hysteresis loss is proportional to frequency and eddy current loss is proportional to frequency square. Otherwise, you have to use their expressions that we took, that PH is proportional to Bm raised to the power 1.6 into F and PE is proportional to Bm square into F square, which is equal to V square. In our next problem, it is saying the percentage resistance and percentage reactance of a 10 kVA 400 by 200 volt 3-phase transformer are 2% and 10%. If constant losses are 1%, what is the maximum possible efficiency? So here there is no concept of 3-phase transformer as such. The efficiency expression remains the same. Now we know copper losses at full load is I full load square into R. Okay. If we take in terms of per unit, I full load will always be 1 per unit, because per unit values are derived after dividing by the full load or the rated values. So if you divide I full load by I full load, you will get 1 per unit. And we will have R is equal to R in PU. So copper losses full load in terms of PU will be equal to resistance in PU, because IPU will be 1. Okay. So for maximum efficiency, we have X is equal to under root Pi by PCU full load. We can keep both of them in per unit. Constant losses are 1%, that is 0.01, and resistance in per unit is 0.02. So this will be 0.707. At this amount of loading, we will have maximum efficiency. Now let us try to calculate the efficiency from the expression that we have studied. Eta will be 0.707 x into kVA. So under per unit system, the kVA rating will be taken as 1 per unit, because when we convert to per unit, we divide it by the rated value. So rated value upon rated value will give you 1 into power factor. For maximum efficiency, power factor will be taken as unity divided by 0.707 into 1 plus constant losses are 1%, that is 0.01, and under maximum efficiency, copper loss will be equal to iron loss, so it will be 0.01 into 100%. So this comes out to be 97.24%. So this is the maximum efficiency of the transformer. Usually transformers have high efficiency. Why? Because they do not have any rotating part. Since they do not have any rotating parts, that is, they do not incur any mechanical or the rotational losses, so their efficiency is higher. In our next problem, it is saying a 10 kVA 400 by 200 volt single phase transformer with percentage resistance of 3%, percentage reactance of 6% is supplying a current of 50 ampere to a resistive load. What is the value of load voltage? Okay. So let us, since this resistance and reactances are given in percentage, let us find the current also in per unit. For that, I will need rated current, and rated current on the secondary side. Secondary side is 200 volt side. So I full load will be 10,000 by 200, that is 50 ampere. So if I want to find per unit current, I will take 50 ampere this current divided by the rated current, that is 50. So it is 1 pu. Now usually the circuit model of the secondary side of transformer is resistance reactance and then load. Okay, here we will have EMF, here we will have load voltage. Okay, this is R and X. Now it is saying that the load is resistive, that means load voltage and load current are in the same phase. So let us assume load voltage is V angle 0, current will be 1 angle 0 in per unit. Okay, so if we apply the equation for the EMF, EMF will be 200 because it is saying rated voltage. So EMF will be 200, that is the 1 angle delta. I am assuming it is 1 angle delta per unit. Why 1 per unit? Because it is the rated voltage, that is 200 volt. So in per unit it will become 1 pu. And I do not know about its phase. Is equal to V angle 0 plus 1 angle 0 into R plus Jx, 0.03 plus J 0.06. Now if we take magnitude on both the sides, or let us take magnitude square, it will be 1 is equal to V plus 0.03 square plus 0.06 square. So V comes out to be 0.97 pu. In actual value it will be 0.97 into 200. On secondary side rated voltage is 200, that is 194 volt. Other method what we can do is we can try using the voltage regulation. So we know voltage regulation is E minus V by E into 100. Now taking in per unit it will be 1 minus V by 1 into 100%, that is 1 minus V. Now this voltage regulation 1 minus V will be equal to I into R cos phi plus X sin phi. Now current is itself 1 per unit, resistance is 0.03, power factor is unity due to a resistive load, so sin phi will be 0, it is 0.03. So V will be 0.97 pu, or it is equal to 194 volt. This can be the other method that you can try. Okay, either you can try using the exact KVL equation in the transformer or using the approximate expression for the voltage regulation. Both the answers will be approximately same. Okay, so that is your choice. But remember, this expression will always give you an approximate answer. So whenever you are attempting a numerical type of problem, it is better to go with the exact method so that your answer is correct up to 2 decimal places at least. Okay, because otherwise you do not know how much error you will encounter while approximation. Moving on to our next problem. It is saying the hysteresis loop of a magnetic material has an area 5 cm square, where 1 cm is equal to 2 ampere turns, one other centimeter is equal to 50 milliweber. So if we calculate area 5 into 1 centimeter into 1 centimeter, 5 into 2 ampere turns into 0.05 Weber. So it is 0.5 ampere turns into Weber. Now we know hysteresis loss is equal to area under the loop into frequency. So it is 0.5 into 50, that is 25 watt. Okay, remember always hysteresis loss is equal to area under the BH curve multiplied by the frequency. Moving on to our next problem, it is saying a 400 by 200 volt by 200 volt. That means if 400 volt is applied on primary, on the next winding it will be 200 and on the other winding it will also be 200. Is connected as shown in the figure. We need to find the reading of voltmeter V. So dot convention shows which terminal will be positive. So this is 400. This will be 200. But here this will be 200. So if we apply KVL, let us move on something like this. Okay. So plus 400 minus 200 minus 200 plus voltmeter V. So if we take voltmeter terminals as plus minus V equal to 0. So V will be equal to 0. That is the voltmeter reading will be 0. Okay. So always remember, whenever you are taking the polarity of voltage, the dots will be taken as positive in all the windings. Okay. Maintain this uniformity, that wherever you see a dot, you will mark it as a positive terminal and the undotted terminal will be marked as a negative terminal. That way you will be comfortable in solving the problems. In our next problem, it is saying a single phase transformer has a maximum efficiency of 90% at full load and unity power factor. So it is giving two informations here, that at full load unity power factor we have a maximum efficiency and the magnitude of maximum efficiency is 90%. Now we know eta is max when x is equal to under root Pi by Pcu full load. It is saying maximum efficiency occurs at full load, that is x should be 1. For maximum efficiency x should be 1. So it implies Pi is equal to Pcu full load. Okay. So if we keep maximum efficiency at 0.9, it will be x is 1. We are talking about full load. kVA cos 5 power factor is also 1 divided by kVA plus iron loss we do not know, but copper loss at full load is equal to iron loss. So if we solve from here, Pi will come out to be 0.055 kVA. Okay, now what it is saying is we need to find efficiency at half load and same power factor. Okay. So for half load, x will be equal to 0.5. So eta will be 0.5 into kVA. It is saying same power factor, that is 1. Then 0.5 into kVA into 1 plus iron loss is 0.055 into kVA plus x square PCUFL. X square is 0.25 into PCU full load is equal to iron loss. So this comes out to be 0.879, or we can say 87.9%. So this will be the efficiency at the half load and unity power factor. So that is how you deal with the problems based on the efficiency. As we have seen that many problems have been asked from the efficiency. So this is a very important topic in case of transformers. Other thing is just the simple circuit solving and the induction in case of transformer. In the next lecture, we will see some few more problems based on this single phase transformer, and then we will move on to our 3-phase transformer.